Hello everyone. So in this section we're going to look at whether anions are going to be acidic or basic. Okay, but first we'll look at anions of weak acids, whether they are going to be bases or acids. So anions of weak acids as weak bases. So what does that mean? Now let's look at this example. The anions of weak acids often function as weak bases. Meaning, if you have a weak acid, for example, let's say HA is your weak acid. HA will, let's say you have a HA weak acid. In the presence of water, it will give you A minus and hydronium ion. Correct? So this one, HA weak acid, which is now giving you hydronium ions, will make it acidic solution. Now let's take this anions of weak acid. So this A minus is going to be your anion. So you put that anion into water. What happened? Now when you put the anion into water, A minus plus H2O, this is your oxygen, H2O. This A minus takes the hydrogen from water and then give you HA plus OH minus. Now this process, anion reacting with water molecule, give you hydroxide ions into the water that make it basic. That's what it says. The anions of weak acids often function as weak bases. Okay, so the base grab a proton from water and add hydroxide ions into the solution, and that will make the solution basic. A solution of HA is acidic. So this one right here that I showed you, HA is acidic because it adds hydronium ions to the water. But if you take the anion of the weak acid HA, A minus, it acts as a base and it grab a proton from the water molecule and produces hydroxide ion. So that solution will become basic. Okay, a solution of HA is acidic while a solution of A minus is basic. Okay, now for example, if you take HF, hydrogen fluoride, which is a weak acid, with water it gives you hydronium ion and F minus, which is an acid because it adds hydronium ions to the water. Okay, HF is a weak acid, much weaker than hydronium ion. So that's why we say that equilibrium lies to the left. This is in equilibrium, but the equilibrium lies to the left, like that. HF is a weak acid, much weaker than hydronium ion. So this equilibrium lies to the left. But the little amount of hydronium ion that you produce because of the dissociation of the HF makes the solution acidic. So HF is going to be greater in acid strength than fluoride. But this hydronium ion that come from the little bit of dissociation of HF is more compared to the hydroxide ion from the autoionization of water, making the solution acidic. That's why a solution of a weak acid is acidic. Okay. Now F minus, the anion. Anion can act as a weak base. Remember the definition of a base, Bronsted-Lowry base is anything that can grab a proton is a base. So fluoride can act as a weak base. Let's say the fluoride source is sodium fluoride. Sodium fluoride is a salt. Okay, you dissolve sodium fluoride in water and it is a salt. It would dissociate into sodium ions and fluoride ions. Okay, So sodium fluoride, it's a ionic salt. It dissociates to give you sodium ions and fluoride ions. Dissolve in water, dissolve completely, and fluoride can act as a weak base. So this fluoride ion react with water to give you HF plus hydroxide ions. So this act as a weak base, and it add hydroxide ion to the solution, making an ion of a weak acid is a basic solution. That's what you are seeing here, fluoride ion with water giving you HF and OH minus. Equilibrium favors the formation of the weaker acid and base. Since HF, although a weak acid, is a stronger acid than water, this equilibrium also lies to the left. Okay, so the two acids that we have here is water and HF. Between these two, HF is a stronger acid compared to water, but so the equilibrium lies to the left. Okay, so if fluoride ion is greater than HF, but hydroxide coming as a result of this equilibrium, even the little amount that coming due to the fluoride reacting with water generating hydroxide, this hydroxide from fluoride reacting with water is greater than the hydronium ion concentration from the autoionization of water makes the solution basic. Okay, so the solution is therefore basic. So pretty much what you need to know is, first identify what is the anion of the weak acid. It reacts with water forming HF and hydroxide ion. If it generates hydroxide ions, that will make it a basic solution. If it generates hydronium ions, that will make it an acidic solution. Okay. Okay. Ka and Kb for a conjugate acid-base pair. Now let's say here you have a weak acid Ha with water giving you H3O plus and A minus. Okay, the hydronium ions. And then you take the anion of the weak acid. It acts as a base, react with water to give you Ha and hydroxide ions. And then we can add these two together. When you add the two together, what's going to happen? So this HA get cancelled when you add the two together. And then you have A minus cancelled. So water and this water molecule make it two water molecules. From this side you have hydronium and hydroxide, these two. So basically two water molecules giving you hydronium ion and hydroxide ion. If you look at the Kc for the overall equation, remember if you have two equations, if you want to find out the Kc for the overall reaction, if this is K1, this is K2, from our previous section we know Kc going to be K1 times K2. Right? So if you write the K1 for the first one, it's going to be K1 for this equation, hydronium ions. Your reactant products are hydronium times A minus over HA. And K2 would be hydroxide times HA, over A minus. You multiply these two together. What happens when you multiply? So here you have HA get cancelled. A minus get cancelled. So you end up with hydronium ions times hydroxide. And this is your Ka and this is your Kb, and it will become Kw. So these are conjugate acid-base pairs. Ka and Kb for a conjugate acid-base pair. Basically Ka times Kb equals Kw. Right? So we came up with this expression Ka times Kb equals Kw for a conjugate acid-base pair. Okay, and this relationship is true for any conjugate acid-base pair. Okay, so let's use this equation to put this concept into practice. Sodium acetate, this is the formula. You can represent it by NaAC. Used in textile dyeing, what is the pH of 0.25 molar sodium acetate at 25 degrees Celsius? The Ka of acetic acid is given. You want to find out the pH of sodium acetate. Ka of the acetic acid is given. Right? So what is the plan? Sodium salts are soluble in water and acetate is the anion of acetic acid. So it acts as a weak base. We write the base dissociation equation and the expression for Kb and solve for hydroxide. We recall that any soluble ionic salt dissociates completely in solution. So acetate ion, initial acetate ion also going to be 0.25 moles. Okay, so we were given sodium acetate. So sodium acetate is a salt. Salt will completely dissociate. Sodium acetate dissociate to give you Na plus ions and acetate ions. So if you started with 0.25 moles sodium acetate, your acetate ion also going to be 0.25. This is also going to be 0.25 because this is a strong electrolyte, sodium acetate. It's a ion, sodium ions and acetate ion will completely dissociate into sodium ions and acetate ions. Okay, now we can put this into equation where we take the acetate ions. It is a weak base of the weak acid, acetate ion with water giving you HAC, which is going to be acetic acid plus hydroxide ions. So this is our base, weak base. So Kb equals therefore HAC, which is acetic acid, times hydroxide over acetate ions. And we can construct ice table for this particular equation. So your acetate ions are going to be 0.25 because I showed you it's a strong electrolyte, completely dissociate sodium acetate. 0.25, we don't have to worry about the water, and acetic acid 0, 0. So the change going to be X amount is going to react. X amount of these are going to form. So at the equilibrium, 0.25 minus X, X, X. Now we were given Ka of acetic acid. We want to find out the Kb. Remember this equation here. Ka times Kb equals Kw. So we were given Ka. Kw is the water, 1 into 10 to the negative 14. So we can find out Kb. Kb would be Kw over Ka. You see, Kb of acetate ion would be Kw over Ka. Kw 1 into 10 to the negative 14. Ka, which is the acetic acid, is given to us 1.8 into 10 to the negative 5. So we can find Kb. So you can plug this number over here for Kb. And we don't know these two. And 0.25 minus X can be considered as 0.25 as our assumption. Okay. So 5.6 into 10 to the negative 10 x squared over 0.25. So you can find out x, which is the hydroxide ion concentration. We can check to see if our assumption is correct. So what is our assumption? Our assumption is 0.25 minus x is almost same as 0.25 because x is negligible amount, right? Where for the acetate ion concentration, it was 0.25 minus x in our ice table. So we found x. So how do you check to see the assumption. You take the X amount, which is this amount, and then you divide it by the initial concentration 0.25. If it is greater than 5%, we cannot use this assumption. Since it's 4.8.10 to the negative 3, you can use the assumption and we are fine. Okay, so the 5% assumption is justified. So we want to find out in this equation, what are we looking at? We want to find out the pH of the solution. What we found out is the hydroxide. So to find out the pH, we need to know the hydronium ions. So hydronium ions times the hydroxide equals Kw. So hydronium ion would be Kw over hydroxide ions. Kw 1 into 10 to the negative 14 and X hydroxide 1.2 into 10 to the negative 5. So the hydronium ion is 8.3 into 10 to the negative 10. So the pH would be negative log of 8.3 into 10 to the negative 10. pH is 9.08. So this is a basic pH, right? Neutral pH is 7. Acidic would be less than pH 7. Basic would be more than pH 7. So we are dealing with an acetate solution. So we talk about acetate or anion of a weak acid is basic solution, which also justifies that having the pH 9.08. Okay, remember in this equation, okay. All right, you see here acetate ion generate hydroxide ion. So the pH also reflected that having 9.2 pH, 9.08. Okay. Now, so earlier we talked about sodium acetate, which gave us a basic solution. Now let's see what are the salts that yield neutral solutions. A salt that consists of the cation of a strong base and the anion of a strong acid yields a neutral solution. So for example, sodium nitrate. So sodium nitrate is a salt. How do we get the sodium ion? Sodium is the cation of sodium hydroxide, a strong base. And nitrate is the anion of nitric acid, which is a strong acid. So then this solution will be neutral because neither sodium nor nitrate will react with water to any great extent. Okay. For example, if I showed you what this means, let's say you have a strong base sodium hydroxide and then you have a strong acid nitric acid. So sodium hydroxide and nitric acid is going to form sodium nitrate plus water. So this is the acid. No, this is the base. Sorry, this is the base. This is the acid and it forms salt and water. Right? So sodium ion is the cation of a strong base and nitrate ion here is the anion of a strong acid. Sodium is a cation of a strong base. Nitrate is the anion of the strong acid, nitric acid. So it forms sodium nitrate and this solution is neutral because sodium nitrate dissociate to give you sodium ions and nitrate ions. And the sodium and nitrate ions, they do not react with water again to give you sodium hydroxide and or nitric acid. So the solution will remain as neutral. Okay. Salts that yield acidic solutions. Excuse me. A salt that consists of the cation of a weak base and the anion of a strong acid yields an acidic solution. Now this is a salt, sodium chloride. Consists of the cation of a weak base, ammonia. Let's say ammonium hydroxide is the form of ammonia. And the strong acid, hydrochloric acid, anion of a strong acid. These two together give you ammonium chloride and water. Ammonium chloride and water. Now this is the salt. How does this salt formed? It came from, ammonium ion came from cation of a weak base. And then the chloride ion came from as anion of a strong acid. That give you acidic solution. How does that happen? Now if you take ammonium chloride, this would generate ammonium ions and chloride ions. This is a salt. Salt will dissociate to give you ammonium ions and chloride ions. Chloride ion, since it's an anion of a strong acid, it's not going to react with water. But if you take ammonium ion, it is going to react with water. Ammonia plus water will make you ammonia plus H3O plus hydronium ions. That will make it an acidic solution. This is the equation I just wrote. Ammonium ions with water forming ammonia and hydronium ions. So this solution will be acidic because ammonium ion react with water to produce hydronium ions. Okay. Salts that yield acidic solutions. Now let's look at iron nitrate. A salt that consists of small highly charged metal cation and the anion of a strong acid yields an acidic solution. Now iron Fe3 plus is a small highly charged metal cation. Nitrate is the anion of nitric acid, which is a strong acid. The solution, this iron nitrate solution, will be acidic because the hydrated iron Fe3 plus will react with water to produce hydronium ions. How does that happen? Remember we talked about this earlier also when I showed you that the aluminum with 6 water molecules, you form aluminum complex. And then in the presence of the water, one of these OH bonds will become more polar and water molecule will grab a hydrogen, generating hydronium ions. And this is similar to what I have showed you here. So instead of iron, here we have aluminum 3 plus. But it's the same thing with Fe3 plus. Iron would take 6 water molecules and then one of the water molecules grab a proton from one of the water molecules, generating you this complex and hydronium ion. It is the same concept. Instead of aluminum, now we have iron 3 plus. Okay. So the solution will become acidic. Over here. Salts that yield basic solution. A salt that consists of the anion of a weak acid and the cation of a strong base yield a basic solution. For example, sodium acetate. Sodium acetate. Acetate is the anion of a acetic acid, a weak acid. And sodium is the cation of sodium hydroxide, a strong base. This solution will be basic because acetate ion will react with water to produce hydroxide ion. So what's happening when you put this into water, sodium acetate, it will give you acetate ions plus sodium ions. Sodium will not react with water because it's a cation from a strong base, but the acetate ion over here react with water to give you acetic acid and hydroxide ion. So as a result, the solution will become basic. Okay. Okay. Let's look at these samples. Predicting relative acidity of salt solution from reactions of the ions with water. Predict whether aqueous solution of the following are acidic, basic or neutral. And write an equation for the reaction of any ion with water. Now potassium perchlorate. Let's look at potassium perchlorate. When you put this into water, potassium chlorate, what's going to happen? So this will dissociate into K plus, potassium ion, and ClO4 minus. How do we make potassium perchlorate? Potassium coming from KOH, which is a cation from a strong base, and perchlorate ion come from HClO4 excuse me excuse me, which is an anion of a strong acid. So this is a strong acid, so this is a strong base. This is a cation, K plus is a cation of a strong base, and perchloric acid is a strong acid, so perchlorate is a anion of a strong acid. Okay. Strong base, strong acid. Okay, so K plus and ClO4 minus is not going to react with water. No reaction with water. So as a result, the solution will remain neutral because potassium is a cation of a strong base and perchlorate is an anion of a strong acid, perchloric acid. Okay. And then sodium benzoate. So let's see what happened to sodium benzoate. You put sodium benzoate into water, it's going to dissociate into C6H5 benzoate anion plus sodium ions. Now this one is a carboxylic acid, which is an anion of a weak acid. Okay, and sodium ion is a cation of a strong base. So cation of a strong base, sodium is not going to react with water, whereas benzoate C6H5COO minus, it's an anion of a weak acid going to react with water, going to form benzoic acid C6H5COOH. Water molecule give hydrogen to benzoate, and what you are left with is hydroxide ion. So it adds hydroxide ions into the water, making it a basic solution. Okay, so sodium benzoate solution will be therefore basic. And then the chromium nitrate. So chromium nitrate, what's happening with the chromium nitrate? It's going to give you chromium ions, Cr3 plus, and nitrate ions. And the nitrate chromium ions, it's a small charged cation. Nitrate ion is an anion of a strong acid. So this guy is not going to react with water, nitrate ion. Whereas the chromium ions can react with water. Remember to give you chromium and 6 water molecules. Just like the previous slides we had seen with iron 3 plus and aluminum 3 plus, chromium also having 3 plus charge, chromium can have 6 water molecules, right? And this chromium 6 water molecules can react with another molecule of water and give you this equation. Once this chromium hexahydrate reacting with water, one of these water molecules give its hydrogen to form hydroxide ion and then releasing a hydrogen, making the solution acidic. Okay, so that solution will be therefore acidic. And these are the explanation of the previous two problems, A and B.